My name is Ever Barbero, and today I'd like to talk about Abaqus User General Section, UGENS. I will use an example of UGENS, called DDM5, that implements discrete damage mechanics. UGENS is a user-programmable feature in Abaqus that allows us to introduce our own material model for shells. The file DDM5, UGENS.std.object, contains the code for a UGENS implementation for matrix damage simulation in laminated composites. DDM5 stands for Discrete Damage Mechanics, version 5, as explained in my textbooks. You should download these files from my website. The file DDM5, UGENS.std.object, is the most important, because it contains the pre-compiled code for a UGENS implementation for matrix damage simulation in laminated composites. The other files will help you set up the simulation. This video uses a modified version of example 9.1 in my Abaqus textbook. The explanation for example 9.1 provided in the textbook is correct, but cumbersome. Here I will explain an easier way to set up the simulation using Abaqus CAE, all the way to finish with an animation of damage evolution in the laminate. These are the geometrical and material properties required by DDM5. The Python script DDM5 write keyword block.py will help you keep track of all this. Formally, the geometrical and material properties for DDM5 should be entered in the input file according to this format, but this is too complex. The Python script DDM5 write keyword block.py will take care of formatting these lines for you. DDM5 uses 3 times n state variables SDV, where n is the number of laminas on the symmetric half of the laminate. State variables are used by UGENS to keep a record of the state of the material at any time, and to return results to the visualization module of CAE. Next, I will set up the simulation, step by step, using CAE.
Okay, first we need a part. So here we have in module part, and we click here to create the part. The part is laminate. 3D deformable shell planar, yes, approximate size 20, that's okay. Now we sketch the edge of the plate, and we make it go from 0, 0, enter, to 10, 10, enter, and once we're done, we have our part, and we say done. And now we have to create a hole in the middle of the part, and so for that, we say cut, shape, cut. What are we going to cut? A circular hole, true, and the plane for the hole is this, and okay, and now we have to see the direction in which the hole is going to be drilled, and it's this direction, it's okay. And so first edge from which to locate the hole is going to be this, and we're going to put it in the middle at 5, enter. And second edge is going to be this, and we're going to put it at 5 in the middle, enter. And the diameter is 4, enter, and we got the hole. Okay, now that we have the part, the next thing we need is to create material properties as a placeholder for the real material properties that we will enter later. So we go to property, and we create material, and this material will be general user material, mechanical, and we put just one property, okay, 0.144. It's just a number, it's a placeholder. Doesn't matter what we put here, we gotta put something, okay? So we got that. Now, same thing with the section. We create a section, and this section, call it section 1, doesn't matter. And then it's a shell, homogeneous, continuous, and then material 1, here we put material 1, and we say okay, and the shell thickness must be specified, so we put some number, 0.144. Okay, it's a placeholder, don't worry about it. And now we have to assign the section. This is important, but be careful. Now we gotta select the regions, and yeah, we select this region, but the name of the set, this is the super important thing, it has to be called whole laminate. okay? And this is going to create a set called whole laminate, and it has to be created here, not some other way. So when I say done, the section is assigned to the part, and a set is created that is called whole laminate. All right, section is section 1, from section, middle surface, all this, okay, done. All right, please don't go and try to create a set in some other way, like tools, set, create. No. If you do it like this, it's not going to put the set right in the correct place in the input file, and then we cannot read the properties for UGENS. UGENS is very picky about this, so you have to do as I say. All right, and so just to re-emphasize what we have done, so in the part, we have laminate, which has sets, and there is this set that is whole laminate, which you see is the entire part, all right, and we have to be created right there, okay, and the features, sure, there is a shell planner with section sketch and cut circular hole, of course, we all know that, and then section, yeah, we got this section, which is a fake section that we put, all right, and then in assembly, we don't have anything because we didn't do it yet, okay, done. Okay, now we need an instance of the part. For that, we go to assembly, and here we say create an instance, and okay, create an instance from part. The part is laminate, dependent, okay, and that's it, it's done. Okay, now we need steps. So from assembly, we go to step, we take the manager, we see there is an initial step already created, but we need another step to apply the strain. So we say create, and this we're going to call it apply strain. And then after initial, general, continue. And then what we have to do is we have to say, okay, put some more here, more steps, 1000. Initial 0.01, the maximum has to be 0.01, so and the minimum we're going to put 0.0001, and then we say okay, and that's it, we have the step. Okay, so now it's a good time to modify the field output request, tools, other output, field output request, edit, this one. So this is to say, tell Abaqus what do we want to save so that we can see the results. And what we need is displacement, reaction forces, and SDV. SDV is the most important thing because that means state variables. And the UGENS and UMAT, they communicate with Abaqus through SDVs for input and output. So if we want the results, we gotta get them on SDVs. And that's it. We put it like this, and that's it. Okay, next we gotta put the boundary conditions. To put the boundary conditions, we have to go here to load, and the manager for boundary conditions, and then create, and the first one is symmetry X, and in what step? In the initial. Always boundary condition we put on the initial, and so here we pick symmetry and then continue, and then it says select region for the boundary condition. Well, symmetry X is here, and it's going to create say 1, done, and we pick X symmetry here, and we're done. Okay, now we create symmetry Y, also an initial, all is the same, go there, symmetry 1 is applied down here, it's going to create set 2, all right, then we pick Xsim, okay, and now we're going to set it up so that we have only membrane behavior and no vertical deformation. Anyway, the laminate is symmetric, so shouldn't have a vertical deformation, out of plane deformation. So create, and we call it membrane, only on the initial mechanical displacement, continue, and then sets. There is some set which we could pick this, and then we pick U3 0 and the rotations also 0, and that's it. And we gotta dismiss this, no. And so now one more that we need is to apply the strain. So this is going to be apply strain. On what step? You cannot apply the strain on the initial, you gotta apply on the second one. Apply strain, mechanical, and that's the displacement. And then we say continue, and then here dismiss this, and select this edge, which is where we are going to apply the strain, and it's going to create say 3, and we say done, and we want a displacement U1, and this displacement is 0.18735. Okay, so okay, like that, and we have everything: membrane, symmetry, and the strain is applied, and this means okay. Next we need a mesh, so we go to this module mesh. And so first we check the element type. Okay, we gotta select the part. Mesh element type. And element type is shell 4R, which is okay. We're gonna use that. Then we check the seed to see how refined the mesh is. And the seed is 1, which will create big elements like this. If that's too big, so we're going to put 0.5, and we check it before we apply it, or we apply just to see, okay, now the elements are going to be smaller, not too small, but smaller, so it's okay. And we do like that. And then we come here and we mesh the part, and it says, okay, to mesh the part, yes. And we got the mesh, it's not bad. Okay, so the next step is to get a job. So we set up a job, we go to the job manager here, and we create a new job. Name of the job, we're going to call it job 1, and the source is the model, which is what we model. And that's it, we say continue, and we don't need to do anything else because we're not going to run this job. I say okay, and then all I have to do is write this file right here and write input. I cannot run this because the material properties we entered were fake. We didn't enter correct material properties for the UGENS that we have. So we write this info file, which is going to be job-1.imp, and then we go now and we modify it. And then we come back here and we run a complete job, which is going to be called job 2. Okay, so then we write the input is written, the job input has been written to job-1.imp, and now we go look at it. Here is job1.imp, and this is the file that is generated by CAE. But in this file, the material properties are those fake material properties that we enter, and we have to change those properties by the properties needed by DDM5 UGENS. And so how we're going to do that? We're going to use this Python code that I prepared for you. You don't have to copy this because this code is in this website. Just go there and download it. And then with this code, for any different case you have, then you enter your properties here. Like for example, here you have a number of laminas, 3. The example I'm doing is similar to 9.1, so 3 laminas. And then you enter, say, okay, modular elasticity, the fiber direction, modulus transverse direction, shear modulus, Poisson, coefficient of thermal expansion, again, fracture toughness mode 1, fracture toughness mode 2. Of course, for this, you have to read the book to understand what all these things mean. Ply thickness, which is not the same as lamina thickness, temperature excursion during the analysis, and then the laminate stacking sequence called LSS in pair of numbers. Like for example, here it says 1 ply at 0 degrees, 8 plies or of 0.144 thickness each at 90 degrees, and then half a ply at 0 degrees. Yes, I can have half a ply from a modeling point of view because I model only half of the symmetric laminate. So there are 3 laminas up to half of the laminate only. And after you enter your material properties, then you don't have to worry all this because this is going to write the file. And now I'm going to run it because this is Python. Now I can run Python inside Notepad++ because I set it up. I have another video where I explain how to do that. And all I have to do is go here, run, and say Python, and it will run Python, and that's the output. So in the output, it says in your input file, that will be job 2. All right, so what we do here is job 1, file, save as, and we call it job 2. Okay, all right, save. And over here we put 2. And this is so that I keep job 1 in case I make a mistake and go back. So this is the job 2, which is exactly the same as job 1, but now I'm going to modify it. And how I'm going to modify it? Okay, I go here, and it says in your input file, comment next 2 lines inserting double star like this. So shell section, whole laminate material 1, these were fake properties, so we gotta comment that. And then immediately after that, we have to enter this. So copy this, and now I go to job 2, and I find, where is this? These are the nodes. These are the elements. Okay, and so here you go. This is these 2 things I had a comment or delete, whatever you like. You can comment by inserting 2 stars in front, like that. And before end part, then you have to insert this, and that's it. All right. And by the way, this is the whole laminate set that I told you before that you have to create, and it has to be right here. Yes, because it has to be defined before you use it. Yes, so you use it after you define it, and for that it has to be generated in the way I show in the video. Okay, and then the next thing we gotta do here, it says immediately above a step I have to put this. Yes, and this is for the initial conditions for the user material subroutine. That means the initial damage that I have to enter. And so we put it here, and we gotta find step. Where is step? Let's see, materials. Here is a step. Right here before step, I gotta put this, done. See, here it is, okay? So save, I have job 2, and so now I can go and run this job, and hopefully it will work. Okay, so now all we have to do is to create a new job, and this job we call it job 2, and it's not gonna be from the model, but rather from the input file. And what input file? The input file that we just created, job 2. And we say okay and continue, and then we have this menu, and now we have to go here and tell what user subroutine to use, which is easy, is this one right there, and then okay, done, and then we have this. So now we have this job 2, and then we submit and start to run. It takes a little while because there are like 400 elements and 64 frames or 64 steps, something like that. So it's gonna take a while. Okay, it's done. And so once this is done, then we can click here results, and then it shows us this, and we see like this. And now what can we see? Well, the crack density on the lamina 0 is 0. Well, really it's 2 10 to the minus 2 because that's the initial damage that we put, but it's uniform, so damage does not grow in the 0 longitudinal layer because the applied strain is in the longitudinal layer and the fibers are taking all the load. But if we go to SDV4, which is the crack density in lamina 2, then we see now that there is a lot of crack density. The red here is 1.89. That's cracks per millimeter. And then, of course, we have crack density here. And in blue, we have 2 10 to the minus 2, which means no crack density behind the hole because I'm pulling this way. And so everything works. Okay. Okay, and finally we have an animation of crack density on the lamina 2 as a function of the applied strain. That is the center lamina 90 degrees that is cracking. And that's it. Thank you very much for your attention. If you have any questions, you can write them as comments or contact me directly. I'll be glad to answer questions, watch my other videos, whatever. This is a complicated topic, so you gotta take it easy. Thank you. Thank you again.